Okay, I'm back and here to talk about our final section. And I was trying not to omit this section. I know I'm not going to do it justice because we just don't have the time, but I did definitely want to expose you to this important theorem and discuss this. Okay. And so this is the fundamental theorem of finite abelian groups. Okay. That's a long theorem. And here's what it says. We're not going to, I don't even know if we're going to get to the proof. We will discuss it and discuss some lemmas and corollaries around it. I don't think we're going to prove it though in class. I just don't think we have the time to dedicate what I would need to prove this, but we're going to talk about other theorems that sort of derive from it and some examples of how to use it. So theorem 11.1, it says every finite abelian group, so every finite abelian group, and as always, you should, pause the video and write this down, is a direct product of cyclic groups of prime power order. Moreover, the number of terms in the product and the orders of the cyclic groups are uniquely determined by the group. Okay, so let's look, just want to take some examples of what this is saying, sort of unpack this. Okay. And so let's say we have an abelian group of order 8. Okay. Well, if we break that down, if we decompose it and write it in its prime factorization, then 8 is 2 to the third power, right? Then we're going to focus on the power. So if we focus on the power, the different ways we can write, so the various ways to write 3 would be, we just write it as 3, right? And then 2 plus 1. And then 1 plus 1 plus 1. Okay. And these are the only ways, if order doesn't matter, right? So 2 plus 1 and 1 plus 2 we're recognizing as the same thing. So order doesn't matter. This is how we can write those. Okay. Well, then we take this and we take this information here, and this will tell us how many different possibilities there are for order 8. And we can write it as z 2 to the third power, which is just z sub 8. We can write this as z sub 2 squared cross z sub 2 to the first, which is just 2, right? And so that becomes z to the 4 cross z sub 2. Or we can write this as z sub 2 cross z sub 2 cross z sub 2. Okay. Now, hopefully you see I'm getting this from how we broke up the powers, right? So what this theorem tells us is that for any abelian group. Okay, here we go. Group of order 8. The group, so no matter what, if you find any type of abelian group that has order 8, that group, I should put that group, hold on. That group has to be isomorphic to one of these groups. Okay. And so you would do, in using this, you would do a little more investigation to see, because again, that's why I did sort of my long little message on that last video talking about the power of isomorphism. If we're saying that any abelian group of order 8, it has to be isomorphic to one of these groups, then that means however many, so out of the 8 elements, however many of those elements have order 4, this other group will have that exact the same amount, whichever properties hold, going back over the properties for cyclic type groups and looking at the properties of cosets and subgroups and things of that nature. So that's what this theorem tells us. Every finite abelian group is a direct product of cyclic groups of prime power order. So it is isomorphic to one of these cyclic groups. Okay. Let's take another example. So what if we have something that's not, well, that's broken up into, that has more than one prime factor. So for instance, let's look at an abelian group of order 36. Okay, so for 36, its prime factorization is 2 squared times 3 squared. Okay, so if we sort of break down each power, then 2 is written as just 2 or 1 plus 1. And we have 2 again, 1 plus 1. So they're going to be, if we think about it in terms of the different combinations, there's 2 ways that we're going to write it over here and 2 ways over here. So there's 4 different. So there will be 4 possibilities. Okay. And so we have z2 squared, z mod 2 squared, cross z3 squared. I'm just going to say 3 squared. You guys know that I mean the subscript. And so that's z sub 4 cross z sub 9. Right? We could have z2 squared cross z3 cross z3, which is z4 cross z3 cross z3. Okay. We could have z2 cross z2 cross z3 squared, which is z2 cross z2 cross z9. Or we could have z2 cross z2 cross z3 cross z3. Okay. And so again, that tells us that every finite abelian group, I'm sorry, you guys, my stylus wants to act up. Abelian group of order 36 has to be unequivocally isomorphic to one of these 4 groups. And again, so I hope you're understanding these examples, but also the magnitude of what this is saying. So if I find any finite group, finite abelian group, any group I want in the world with order 36, I am taking that group and basically breaking it down to one of these 4 choices. Okay. That is amazing. Okay. It could just be me and my excitement. It's okay. All right. So we have that. You might want to I just wanted to make some notes about this theorem for you guys to keep in mind. So again, you may want to pause this because I'm just going to sort of go through each of these bullet points. The first is that this theorem reduces questions about finite abelian groups to questions about cyclic groups. Okay, because that's basically what we're doing when we look at our mods. Since every cyclic group of order n is isomorphic to Z mod n, right? This theorem shows us that every finite abelian group is isomorphic to a group of the form that we just looked at in those examples. Okay. As an application, this can be used as an algorithm for constructing all abelian groups of any order. Okay. So this could be some type of programming. Clearly, we can see distinct isomorphism classes. And so here, for instance, we know clearly that Z9 cross Z3 will not be isomorphic to Z3 cross Z3 cross Z3. Okay, although they have the same order, but it's clear here we're going to have an element of order 9, and we won't have that over here. So the key in remembering this is remembering this sort of format right here. If you can set up, let's say, A cross B, A cross B is isomorphic to A cross C if and only if B equals C. Okay, and so this is looking at, if you think about it, this is basically using the cancellation property. Okay, that's what that's saying. All right. And so what that tells us is that Z4 cross Z4 cannot be isomorphic to Z4 cross Z2 cross Z2, because if we were to use that left cancellation, we clearly see and know that Z4 is not isomorphic to Z2 cross Z2. Okay. So again, these are some things just to keep in mind when we're looking at this. Okay. I think I have another example. Yes. This example is actually already completed. It's in your book. I just want to make sure you understand. And you should actually, before you look in the book for the answer though, I just sort of set up the beginning. The last slide actually breaks down the answer. So if you want, it would be nice to practice. So G is a set under multiplication. I should say G is a group under multiplication of mod 65. And G has... well, let me change that. So we could say this is a finite abelian group. You can check it if you want, or you can just trust that it was set up right. This is not letting me. I'm gonna do this. Finite abelian group. It's under multiplication, as you can see, because 0 isn't there, right? But you see 1. So it's under multiplication mod 65. And so these are the elements of G, of this finite abelian group. We can see, just count up the elements, that the order is 16, which is, this looks like a 24, but this is actually, that's 2 to the 4th. Okay, why does that? Let me make it, there we go, 2 to the 4th. And so we can break down 4 as 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. We've done this before, this breakdown, this dissection. So make sure you remember, don't miss out on, you see that 2's there. Be careful that you don't miss any combinations when you sort of decompose or dissect that power. So that means that there are 5 possible isomorphic groups that this G could be isomorphic to. Okay. And I wrote it down somewhere else. So the different isomorphic possibilities, that different groups, would be Z16, Z8 cross Z2, and that's after we've simplified it. Z4 cross Z4, Z4 cross Z2 cross Z2, and Z2 cross Z2 cross Z2 cross Z2. Say that 5 times fast. Okay. And so those are your possibilities. Now, they actually computed the orders for you. Of course, you won't be necessarily given this on a quiz or an exam. However, I probably wouldn't have maybe as many elements just to simplify your life, or maybe I would. I don't know. I wouldn't. But anyways, notice the different orders. So automatically, because again, we're trying to see which group is this, which direct product is this group isomorphic to, we can clearly eliminate, let me erase those. What can we eliminate? We can already eliminate Z16, Z8, and that last one, right? Because we see all our elements are order, besides the trivial element, it's order 2 or 4. Okay, so because knowing that information, and there's other things, other properties that you could look for as well. Sometimes it's not as easy to compute all the orders. That might take a long time to do. Sometimes it's easier to maybe look at subgroups to see if there are similarities or differences in terms of elimination. But we've just taken, well, first of all, we simplified our life because we took some generic abelian group of order 16 and we basically knocked it down and said, okay, it's going to match up with one of these 5 choices. Okay. Then from there, we said, well, by looking at the order of their elements, we can knock off 3 of these choices. So we really are just left with these 2. So why don't you try to see between those 2 what other information you can look for, maybe with elements, that will tell you what's your final answer. So think about that before you go to this next slide. Okay, you've thought about it, I'm assuming. So again, we eliminated Z16, Z8 cross Z2, and all the Z2, 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 Z2 because of the order of the elements, leaving those 2 choices there. Okay. Now you still need to do, so further investigation actually tells us that we will have more than 2 elements in Z4 cross Z2 that's going to have an order of 2. So note here in this group G, there are 3. So I guess we should say more than 3 elements then. So mark that off, more than 3. Okay, so I just added 2, 0, 0, which will have an order of 2. Okay. So that gives us 1 more than we had in G. But your book, you actually can look in your book. I think they explain it a different way, maybe a little more formally in determining that, in case you maybe couldn't think of elements that will give you order 2, that more than 3 elements that will give you order 2. But anyways, you have to do some further investigation. And so therefore we conclude that G is isomorphic to Z4 cross Z4. Okay. We are done. We will continue this discussion in class on Friday, and I will see you guys soon.